Welcome to the Deep Dive, where we extract the most important nuggets of knowledge from a stack of sources, ensuring you're always well informed. Today, we're diving into something pretty fundamental, really, how we get from A to B.
Right. From a starting point news to a goal G, as the computer scientist might say.
Exactly. And, think about it. Whether you're trying to navigate, say, Cambridge streets, or maybe solve a really tough problem at work, you're constantly trying to figure out the best way forward. How do you do it? Usually your eyes, maybe some intuition, they get you a pretty good path, right? And pretty fast, too.
Yeah, usually. We're quite good at that visually.
But what if you don't have eyes? What if you're a program? Or what if pretty good isn't good enough? You need the optimal path.
Now that's the challenge.
So that's what we're digging into today. The core idea is search. And not just Google search, like you said, but search as this basic process, making choices, looking at options, solving problems. Our mission, then, is to really get under the hood of different search strategies, how they work, why maybe one's better than another in certain situations, and, fascinatingly, how these computer science ideas actually model how we might think, too.
It's a really universal thing, this navigation problem, and the solutions vary wildly. Maybe you think about it like taking a cab.
Okay.
You could get let's call him the thief driver.
Yeah.
Takes this awful winding route, gets you there, eventually.
Right, you feel ripped off.
Then there's the honest beginner, does a decent job, safe, follows the rules, but maybe takes a few unnecessary turns, not the quickest.
Okay, the pretty good path again.
Yeah. And then you have the real expert, the PhD, maybe, who knows, every shortcut, every traffic pattern, finds the absolute best, most optimal path.
That's a great analogy. It covers the whole spectrum. And it's amazing how our brains do that pretty good thing so fast, even if we don't fully understand how.
We really don't. Not completely.
But for programs, you need rules, explicit steps. So how do programs start making choices if they can't just see the answer like we do?
Right. When you take away that intuition, it boils down to algorithms. And maybe the most basic, though really inefficient one, is what our sources jokingly called the British Museum approach.
Yeah, I saw that. They said it was a slur against at least the British Museum, if not the entire nation. Why so bad?
Well, because it's just exhaustion, pure brute force. This method literally finds every single possible path from the start to the goal.
Every path.
Every path. You can't really optimize it or be clever because the definition is you have to find everything.
So it guarantees finding a solution, I guess. And maybe all of them.
It does, yes. But the time it takes.
Yeah.
It's just astronomical for anything non-trivial. No room for cleverness.
Okay, so thorough but totally impractical most of the time. Does it ever get used?
Maybe for the absolute tiniest problems imaginable. Otherwise, no. But it's a good starting point conceptually.
Okay. So moving on from just trying everything, what's a more focused way? We read about depth-first search. Sounds intense.
It is quite different. Depth-first search, it sort of barrels ahead in a single-minded way.
Barrels ahead.
Yeah. It picks one path, maybe based on alphabetical order if nodes have names, or just a rule like always go left first. And it follows that path as deep as it possibly can. Until it either hits the goal or it hits a dead end.
Okay. So what happens at a dead end? It can't just give up, can it?
No. And that's the key. The crucial idea here is backtracking. If it hits that dead end, the search essentially backs up to the place where we last made a decision and choosing another branch.
So it retraces its steps to the last choice point and tries a different option.
Exactly. And when you implement this, say, with a list or a queue of things to explore, the new options generated right after making a choice go to the front of the list.
So they get explored immediately, keeping that deep dive going.
Precisely. It keeps that plunge downwards going as long as possible.
Now, the material mentioned backtracking is kind of an optional add-on in theory. What does that really mean? Surely you need it.
Well, theoretically, you could define a search algorithm that just stops and fails at a dead end. But, practically speaking, you'd be pretty stupid not to use backtracking if you actually want to find a path. Otherwise, you just get stuck permanently.
Right. Makes sense. So this depth first, barreling ahead, backtracking, it sounds like it could end up taking some really weird long routes sometimes, a bit like that thief cab driver.
Oh, absolutely. It can produce very roundabout paths if it goes in a long, wrong turn first.
Okay. So, contrasting that deep dive, we also have breadth first search. That sounds calmer, more systematic.
That's a good way to put it. Breadth first search works very differently. It explores the search space level by level.
Level by level. How does that work?
It looks at all the options 1 step away from the start, then all options 2 steps away, then 3 steps away, and so on. It examines everything at the current depth before going any deeper.
And how does the implementation reflect that, if depth first puts new things at the front of the list?
Breadth first puts new paths at the back of the list, or queue.
Ah, okay. So it ensures everything at level 1 is checked before level 2 and level 2 before level 3. Very orderly.
Exactly. Systematic.
But we also read this can be incredibly stupid sometimes. Why would that be?
Well, the basic version, without any improvements, can be really inefficient because it might explore paths that end up at the same place multiple times.
Oh, right. Like finding one way to get to point X, exploring from there, and then later finding a totally different path that also leads to X, and exploring from X all over again.
Precisely. You get an awful lot of search, tons of duplicated effort, especially in complex maps where there are many ways to get to the same spot.
So if depth first is sometimes the meandering thief, maybe breadth first is our honest beginner driver. Systematic will probably find the shortest path in terms of number of turns, but maybe does a lot of extra driving around the block to check every option.
That's a pretty good analogy, actually. It will find a solution, often the one with the fewest steps, yes.
Right.
But potentially with a lot of wasted effort exploring redundant paths.
Okay, so these are the basic uninformed methods, but obviously we want search to be smarter, right? How do we make these things more efficient? That redundancy you mentioned seems like a big target.
It absolutely is. It's
Yeah.
probably the single biggest issue with the naive versions of both depth first and breadth first. They just waste so much time extending paths that go to the same node more than once.
It sounds computationally expensive, so what's the fix? Is it complicated?
Actually, no. It's conceptually quite simple and incredibly powerful. You maintain what's called an extended list.
An extended list.
Yeah, basically a list of all the nodes you've already fully explored, meaning you've already generated all possible next steps from that node. Before you extend any path, you just check.
Mhm.
Is the node at the end of this path already on my extended list?
And if it is,
You just discard that path, don't explore it again. You've already been there and done that, essentially.
okay. So it's like giving the algorithm a memory. Don't explore from X again. We've already covered it.
Exactly. Our sources say you would never not want to do this. It's a fundamental optimization.
Makes perfect sense. It stops that endless looping or re-exploring. I wonder how often we do that in our own thinking. But, okay, memory's one thing. What about giving the search some actual direction, like a sense of where the goal is?
Right. That takes us into the realm of informed searches. These are the smarter strategies that use heuristic information.
Heuristic, like a rule of thumb.
Exactly. An educated guess. Often, it's an estimate of how close are we to the goal from the current point. It's not guaranteed to be perfect, but it provides guidance.
Okay, so let's give depth first a heuristic. What does that look like? We read about hill climbing.
That's the one. Think of hill climbing as depth first search, but with a compass. Instead of picking the next path arbitrarily, maybe alphabetically,
Yeah.
it always chooses the step that looks like it moves closer to the goal, according to that heuristic estimate.
So it's always trying to go uphill towards the goal, hence the name.
Precisely. And in terms of implementation, when it generates new paths, they still go to the front of the queue, like depth first.
Okay.
But they're sorted first, based on that heuristic value. So the path that looks most promising, closest to the goal, gets explored immediately.
That sounds much more direct. Like our cab driver constantly checking the GPS for the road that cuts the most distance right now. It should lead to a straighter path, usually.
Generally, yes.
Mm-hmm.
The sources show it dramatically reduces the number of nodes you need to explore compared to basic depth first. It really highlights that if you have some kind of heuristic, well, you should probably use it.
Makes sense. Okay, so what about the breadth first side? How do we make that informed? Is there an equivalent?
There is. It's called beam search.
Beam search. Like a spotlight?
Kind of, yeah. It's like breadth first because it tends to explore level by level. But here's the key difference. At each level, it deliberately limits the number of paths to consider. It sets a beam width.
A beam width. Like say only keep the best two.
Exactly. Maybe it only keeps the two paths whose endpoints are currently estimated to be closest to the goal. All the other paths at that level, it just throws them away, prunes them.
Wow, that sounds quite aggressive, but potentially very efficient. Our honest beginner driver now only looks down the two most promising streets at each junction.
It's definitely smart in that sense. It avoids wasting time exploring directions that seem to be heading away from the goal. Much more efficient than plain breadth first, which would keep exploring all those paths.
Interesting. And there was one other mentioned, best first search. How does that fit in?
Best first is slightly different again. It doesn't strictly stick to levels like breadth first or beam search, nor does it plunge quite like depth first. Instead, it looks at all the unexplored endpoints of all the paths. It's started all the leaf nodes across the entire search space.
Okay.
And it always chooses to work on the leaf node that currently looks closest to the goal, according to the heuristic.
Ah, so it might jump around quite a bit, working on one branch, then suddenly jumping to a totally different branch if that one looks more promising.
Exactly. It's quite nimble, always focusing its effort on the current best bet anywhere in the search tree.
Okay, so these informed searches sound much better, but journeys aren't always smooth, right? Even with a compass or a spotlight, you can still get lost. Do these smart strategies have weaknesses?
Oh, absolutely, especially hill climbing. Despite its apparent cleverness, it can fall into some really classic traps, particularly when the landscape of the problem isn't simple.
Landscape.
Yeah, think of the search space as a terrain and the heuristic value, like closeness to the goal, as the altitude. You're trying to get to the highest point, the goal. Our sources use a great mountain climbing analogy. Imagine you're climbing in thick fog.
Okay, I'm on a foggy mountain using hill climbing, always taking the steepest step up I can find. What goes wrong?
First, you might hit a local maximal.
A false peak.
Exactly. You climb up a smaller hill. From the top of that hill, every single step you could take goes downwards. So, according to your always go uphill rule.
I stop. I think I've reached the summit.
Right. Even though the real higher summit might be somewhere else entirely, hidden in the fog, you're stuck on a suboptimal peak.
That's a classic problem. I can see how that would happen. What else?
Then there are flat lawns, or sometimes called the telephone pole problem. Imagine a large, perfectly flat plateau, like maybe the shoulders of Mount Washington they mentioned, where apparently people have frozen because they got lost there.
Okay, a big flat area.
If you're in the middle of it and you check all the directions around you, none of them go uphill. They're all flat.
So the hill climbing rule gives you no direction.
None whatsoever. You're stuck. You don't know which way to go to get off the plateau and find an upward slope again.
That sounds paralyzing for an algorithm. And dangerous in the real-world example. Is there another one? Something about ridges.
Yes, the problem of sharp ridges. This one's a bit trickier to visualize, especially in many dimensions. But think of a very narrow, steep ridge leading upwards.
Like an arête.
Exactly. Now, imagine your algorithm only checks steps directly north, south, east, west. If that ridge runs, say, northeast.
Then north, south, east, and west might all lead slightly downhill off the crest of the ridge.
Precisely. So even though you're on a path leading upwards along the ridge, your limited local search directions fool you into thinking you're at a peak, because N, S, E, W all go down.
Wow. Especially tricky if you can't check every possible direction, only a few.
And that gets much worse in higher dimensional spaces where you have many more directions than just N, S, E, W.
It really shows that even a seemingly smart strategy can be completely fooled if the problem structure is complex. It's a good warning for any kind of problem solving, really.
Absolutely. Understanding these limitations is critical. And of course, people have developed more advanced techniques like simulated annealing or genetic algorithms to try and escape these traps, often by adding some randomness or exploring multiple points at once.
Right. It's an ongoing challenge. So bringing this back,
Mm-hmm.
what does all this mean for us, for humans? Does our brain actually run things like depth first or hill climbing when we say, make a plan or decide something?
Well, it's hard to say definitively, but the parallels are strong. When you make a plan, aren't you essentially evaluating a bunch of choices and seeing how they work? That sounds a lot like search, doesn't it?
It does, yeah. Exploring possibilities, maybe backtracking if an idea doesn't pan out.
Exactly. These algorithms aren't just abstract computer code. They're models for certain kinds of intelligent behavior, for problem solving.
And that leads us to something really fascinating mentioned in the sources, an AI system called Genesis that uses these ideas to understand stories, like really understand them.
Yes, this is pretty cutting-edge stuff. The Genesis system reads stories, like Shakespeare's Macbeth, in natural English.
Wow.
It builds up this complex network, an elaboration graph, representing the events, the characters, their relationships, their motivations.
Okay, a map of the story's meaning?
Kind of. And then here's the key. It uses search algorithms running over that graph to find patterns, higher-level concepts.
Patterns? Like what? Can you give an example for Macbeth?
Sure. It can identify revenge. It searches the graph and finds the pattern. Macduff killed Macbeth because Macbeth angered Macduff by killing his family. That structure signals revenge.
Okay, that makes sense. It's finding a known causal template.
Right. Or it can detect a Pyrrhic victory. It searches for the pattern where, everything seems to be going good at first and then not so hot.
Like Macbeth wanting to be king.
Exactly. Macbeth wants to be king. He murders Duncan. He becomes king. She's good for him. But then it all unravels, and he gets killed as a direct consequence.
Yeah.
That fits the Pyrrhic victory pattern.
That's incredible. It's not just finding facts, it's finding these abstract concepts within the story structure using search.
And it allows the system to answer really complex why questions. If you ask it, why did Macduff kill Macbeth? It can give you the immediate reason Macbeth angered him, but also the higher level concept it found. This looks like an instance of revenge.
So it can reflect on its own findings.
Yes.
Yeah.
It can answer on a common sense level, based on direct links in the graph, and on a reflective level, by reporting the patterns it discovered through search. You could explain, why did Macbeth kill Duncan too? Because Macbeth wanted to be king, and Duncan was the king. Simple motivation pattern.
That's really something. It shows search isn't just for maps or games. It's fundamental to understanding complex information, even narrative and human motivations.
Absolutely. And the source material mentioned, this is very recent work, parts finished just last spring, finishing touches added this morning, which is kind of amazing.
Wow. Okay, so we've gone from the brute force of trying every path through smarter but sometimes flawed informed searches, all the way to AI using search to understand Shakespeare. Quite a journey.
It really covers a lot of ground.
And the takeaway for you listening: these ideas, making choices, evaluating options, using heuristics, backtracking, being aware of potential traps like local maximizers, they aren't just for computer scientists.
Not at all. They're fundamental to how we all navigate the world, solve problems, make decisions every single day, whether we realize it or not.
So here's a final thought to mull over. As you go about your day-to-day, maybe pay attention to how you're making decisions or tackling problems. Are you kind of plunging ahead down one path, like depth first, maybe having to backtrack when you hit a wall? Or are you carefully scanning all your immediate options before moving forward, more like breadth first? Are you using some internal heuristic, always trying to take the step that feels closest to your goal, like hill climbing?
And maybe ask yourself, could you be stuck on a local maximum, convinced you found the best way, when maybe, just maybe, a better option exists if you explore it a bit differently?
What kind of search are you running right now?